Hi, class. First off, before I start the physics, let me apologize today for not being able to do a live lecture. Hopefully, everything will work out. On Monday, there's going to be 4 problems or so on this material that I assign after this lecture, and I'm going to post the slides for this whole section this afternoon. That being said, my plan right now is to use Monday's class time as help for the problems because this does happen to be like a more mathematical section. So that said, if it's something that, if you've taken chemistry, it's probably something you've seen before. So today I plan to do the, cover the Bohr model of the hydrogen atom. So in particular, we want to focus on at least the basic ideas about how we fix this problem we have with our model of the atom that we discussed at the end of last class. So as you can, if you remember from last class, due to conservation of energy and the fact that the accelerating electron will produce light and give off energy, the electron in the hydrogen atom, according to our classical model, is going to consistently lose energy. And as it loses energy, it's going to slowly spiral in a smaller and smaller orbit until it collapses into the nucleus. And this is, of course, a problem because it would mean matter is not stable, and none of us would be here to talk about it. So we want to figure out how we can fix this problem. And the main thing we need to consider are the wave properties of the electron, the wave properties of matter. That's going to allow us to create a model of the electron and a model of the hydrogen atom that is stable and doesn't collapse. So this really, the science into determining a correct model for the hydrogen atom is really spent a lot of time in the early 20th century of physics. The story of the hydrogen atom is a very radical solution, but was one among many at the time. So what I want to highlight here is that if the electron is a wave and it's stuck in a bound state around the hydrogen atom proton, we need to consider the wave properties in determining what type of orbit it can be in. This two-dimensional picture is called the Bohr model of the hydrogen atom. And so the idea here is that instead of the electron just as a particle orbiting around the proton, the electron's effective wavelength, as given by the de Broglie formula, determines what type of orbit we can have. So in particular, it's a lot like our problem from earlier in the semester of looking at standing waves on musical instruments, in strings or in wind instruments. Since the electron has this wave-like property, a full number of those wavelengths must fit into one orbit, just like we have to have a full number of crests and troughs inside on the string of a guitar. So what this means is that if we take the total circumference of the electron's orbit around the proton, that has to be an integer number of wavelengths. So whatever the de Broglie wavelength of the electron is, the only orbits the electron can possibly take have to be integer multiples of that wavelength. So, and that's so we could kind of complete, if you can see here, as the electron wave goes around the orbit, it needs to eventually connect up back with itself in a smooth manner. So the main goal in fixing the problem with the hydrogen atom is to treat the electron almost like a standing wave on a string. So before we get into the hydrogen atom problem, I want to go back and review the results from standing waves on instruments. So here, just as a reminder, here we have a string that's tied down at 2 ends. And there's a longest possible wavelength that can fit on the string. That wavelength is shown here in this first box. So the longest possible wavelength that fits between these two ends is has a wavelength of 2 times the length of the string, because we fit half of a wave on the string. All of the other wavelengths that are allowed are multiples of that. So for instance, the second wave that we have here will have the wavelength will be 1 times the length of the string. The third wave that's shown here will be, the wavelength will be 2/3 the length of the string, so on and so forth. The frequencies follow the reverse trend, so the frequencies increase and they're all multiples of the first fundamental frequency. So if we know the speed of the wave and the wavelength for the fundamental, we can find the fundamental frequency, and all these higher waves are just multiples of that. We're not going to be able to find the fundamental frequency for our de Broglie wavelength for the electron, but this idea still determines the idea of standing waves that have to fit in a space is what's going to determine the type of orbits an electron can have in a hydrogen atom. So as a reminder of our end result here for the standing waves on a string, all of the allowed wavelengths were fractions of the fundamental, where in the denominator here we have the number of the harmonic. So m equals 1 is the first allowed wave, m equals 2 is the second allowed wave, m equals 3 is the third, so on and so forth. So we're going to make an analogy to our hydrogen atom problem. Instead of the hydrogen atom, we're going to almost treat the electron wave like it's on a string around the atom. Instead of there being a length and it's tied down at 2 ends, we're just going to bring the string and tie the 2 ends together. And what we could call our boundary condition will be that we have to have a total number of waves fit into the orbit around the hydrogen atom. So after this kind of review of standing waves on strings, what we can think of here is now our electron is in some orbit. And we just kind of take a starting point. We could say that this node here. The electron wave has to go around, it's a node here. By the time it gets back, by the time the electron wave gets back to its starting point, it needs to also be a node again. So it's like the string is fixed to be tied down at these 2 different neighboring points. So it's very much like a standing wave on a string. So what this means is that an integer number of wavelengths has to fit in the length of the string, or conversely, the length of the string has to be equal to an integer number of wavelengths. Here, the length of the string is the circumference of our orbit. This number n here is just a number that counts our different allowed waves, just like m in the last problem. Here we're going to use n instead to not get it confused with the electron mass. So what this number n gives us is it tells us just like we can't have just any number of waves or any wavelength that will fit on the string of a guitar. We can only have certain wavelengths. Here, we can only have certain sized orbits in the atom. This means the electron cannot take just any old orbit. It can only take specific ones that correspond to these different orbits that are an integer number of wavelengths in size. And what this means is that just like there's a smallest or a longest wavelength wave that fits on a string, the fundamental wavelength or the fundamental frequency, there is a fundamental orbit for the electron, and the electron can't take smaller orbits than that. And that will be for this value of n equals to 1. The fact that this model gives us a lowest possible orbit where the electron cannot go lower prevents the electron from collapsing into the nucleus, thus creating a stable model if we take into account the wave properties of the electron and the fact that it forms a standing wave around the nucleus of the hydrogen atom. This model has a lowest possible orbit, and thus the electron won't collapse into the nucleus. So it fixes our fundamental problem, but what we really want to see to determine if this model can possibly be accurate is if it could predict some properties of the hydrogen atom that we know from experiment. So that's what we're going to look at as we move forward. So here's our initial condition for our standing wave for our electron. This is the main condition of our model. The only thing we're going to do here, we now need to kind of take this fundamental relationship and start combining it with other things we know to get a set of predictive formulas that allow us to predict properties of the hydrogen atom. There's going to be a lot of like formulas and algebra in the next few slides, but I'm going to do my best to box the end results and the formulas that you'll need for problems. So here, what I'm going to do, from de Broglie's hypothesis, we can get an estimate of the electron wavelength in terms of momentum or velocity. So I'm going to take this and plug it in here. And that gives us a relation between the speed of the electron and the radius of the orbit it's in. And n here is our counting number for the different allowed waves. So n goes 1, 2, 3, just integer values. M is the mass of the electron. So what we can see here is that rewriting in this way, the electron can only, since it can only have these certain orbits that fit an integer number of wavelengths, when we plug in the de Broglie relationship, what it tells us is that the electron can also only have specific speeds in these orbits. And these speeds are multiples of this quantity h divided by 2 pi, mass of the electron times the radius of the orbit. So we don't know the radius of the orbit yet, so we can't really use this formula for anything yet, other than it tells us that just like there are only specific allowed orbits, the electron can only have specific allowed speeds. It can't just take any speed. So that's the only thing to really take away from this formula at the moment. We can go a step further if we kind of connect to some other old physics we know from last semester. Here, in the Bohr model of the hydrogen atom, we make the assumption that isn't a perfect assumption, but it's a decent approximation for hydrogen. We're going to assume the electron's stuck in a circular orbit. This means that we can relate the centripetal force formula and the electric Coulomb force formula, set them equal to each other. What this gives us when we plug in the different relationships we know for centripetal force and for the Coulomb force, it gives us a second equation for v, the velocity of the electron, and the radius. And combining this equation here with this one up here will allow us to get separate formulas for both v and r that we can solve. So there's a lot of kind of algebra and combining formulas here. I'm going to run through it kind of quickly in the lecture and show you the result. These slides will be posted on Canvas, so you can kind of follow through the algebra if you are one of the people that are so inclined. But really just note what I'm going to do. I want formulas for both v and r. So I have two equations with two unknowns here, and I'm going to try to get one equation for r that I could solve in terms of a bunch of constants. And that will give me the allowed possible orbits, the radius of the allowed possible orbits of the electron. So we're going to go and combine these two formulas. So here they are. And just gonna have to trust me on this. You do not need to copy this down yet. But eliminating v from the problem. So for instance, I could take this second equation, square both sides, and then set. So what I'm doing here, I'm going to square v. And I'm going to square this whole thing. And then set these two equal to each other, the two right-hand sides. And then I'm going to go through a lot of work to solve for r. After we do that, what we get here is this equation for the radius. And we see that the radius, there are only certain allowed radiuses or radii that depend on n. And they also depend on the electric force constant k, the mass of the electron, the charge of the electron e squared, and a bunch of other constants, Planck's constant, pi. The quantity 1 over 4 pi times the force, Coulomb force constant, is sometimes written as epsilon naught. But again, you're not going to have to use any of this for now. But I just want to show you that just like for here, the takeaway message from this formula is that the specific allowed orbits for the electron means that we only have certain allowed speeds for the electron, and we only have certain allowed distances from the nucleus. That's what r gives us. If we set n equals to 1, that's going to be the closest the electron can possibly get to the nucleus. And this is sometimes called the Bohr radius of the hydrogen atom, or Bohr's prediction for the radius of the hydrogen atom. It's given the symbol a sub b. And if you plug in all of the constants, these are all constants that we know: Coulomb force constant, Planck's constant, mass of the electron, charge of the electron, pi, we can get a number. And what we see is that this radius is about 0.0529 nanometers. So it's exceptionally small fraction of a nanometer. And this gives an estimate of the radius of the hydrogen atom when the electron is in the closest orbit possible. So if the electron is this, once the electron is in this orbit, it has lost all of the energy it can possibly lose. It'll still have energy and it will still orbit here, but it can't get closer to the nucleus. So it will never collapse. It will just keep this energy at this point. Whatever energy it has, it will keep it. So this is often also what's called the ground state of the hydrogen atom. The lowest possible energy the electron in the hydrogen atom could have, it has when it's at this radius away, and it doesn't get any closer. Once we know this radius, the radii of the higher orbits, or the higher, what we sometimes call energy levels for the hydrogen atom, are just multiples of that. So if we want the second orbit, the radius of the second orbit, we can take this formula and plug in n equals 2. So luckily here, rarely do you ever have to go back to this big complicated mess. If you compute it for just the lowest radius, this becomes a constant we can use. And the higher allowed orbits are just n squared times that number. So I know there's like a lot of stuff going on here, but the only formulas you really have to use are these two down here, boxed in thick red. We can also take this and find the formulas for the allowed speed of the electron and simplify quite dramatically. So we can compute the speed in the lowest possible orbit. And here that's 2.19 times 10 to the 6 meters per second. And so the speed of the electron decreases the further away as you go into higher orbits. So as you make n bigger, the speed drops. So these are some predictions for things that we can't necessarily measure, but they all have the properties that we would like. So we have a minimum possible distance from the nucleus. We have a minimum possible energy the electron could have, and it can't lose anymore. So this model has the properties we want in that the hydrogen atom will not decay and collapse in on itself. However, the last step is really to take these relationships and use them to predict something we can measure, to see if we're correct about to see if this model, it models things the way we would like, but we need to compare it, of course, to something we can experimentally measure. So that's really the last step here. So, and one thing we can measure, or we can see, is we can see changes in the electron's energy. Because as the electron changes energy, we found out, as electrons gain and lose energy, they give off light. So for those of you that have taken chemistry, you may have done experiments where you looked at the emission and absorption of hydrogen gas, and that's all something that we can see and measure in the gas. We could predict the energies and thus the frequencies and thus the colors of the photons hydrogen gas should emit or absorb with these formulas. And then we could compare that to what we see in the lab. And it all starts from looking at the energy in the electron. So here we could look at and try to plot the energy from, say, the electrons in orbit n. And we could write out the total energy, kinetic plus potential. And even though we didn't cover this in class this year, but you can write the potential energy for two charges separated from one another using the formula shown here. It's not something we cover in Physics 102, but you'll just have to take it on faith from me now. We're not going to end up using this formula, but what we're going to do is take this and then use it to get a relationship for the frequencies and wavelengths of the photons the hydrogen atom should absorb or emit. So the first place to start, is that simplifying this, is to figure out what the different allowed energies are for the electron. And without going through all of the algebra, we could take those formulas we had for the allowed speeds and the allowed radii for the electrons and plug them into this energy formula and get a formula for the allowed energies. So the way you read this here is that if the electron is in the nth orbit, so the first allowed orbit, the second, the third, so on and so forth, the energy it has is proportional to 1 over n squared times a constant. So a bunch of constants here: force constant, electron charge, and the Bohr radius. So the energy of the electrons, so in the lowest possible orbit, that's n equals 1, the electron has a total energy of minus 13.6 electron volts. if the electron is in the second allowed orbit, a bit further away, we have to plug in 2 for n. So the energy is 1/4, or 1/4 times minus 13.6 electron volts. So what we see here is that when the electron is in the lowest energy, and they're the orbit that's closest to the hydrogen atom, it has the lowest energy. The energy is negative. Don't let that bother you. That's just due to the potential energy term here being negative. What that means is that the negative energy means the electron is bound and stuck to the proton. As the energy gets closer and closer to 0, it means that we're getting, the electron is getting closer and closer to escaping from the atom. So as we increase, as we go to further and further away orbits, as we go from orbit 1 to orbit 2 to allowed orbit 3, the energy decreases and the energy gets closer and closer to 0. It's a negative number that gets smaller. So as the electron jumps between these different orbits, its energy changes. And those changes in energy are all due to either emitting or absorbing light. So if we can kind of draw this picture here, it's probably worth just kind of looking at what these things look like. So the different orbits all have specific energies. And they are called, in hydrogen atom terminology, energy levels. And as the electron jumps between these levels, the only way it can do so, the only way it can jump from the close orbit n equals 1 to the next further out orbit, is to absorb a photon of light. So only a photon with that correct energy difference, that correct frequency, can be absorbed and cause the electron to change orbits. If, of course, the electron started in the higher orbit, we had an excited hydrogen atom, in order to fall down to the lower orbit, it would have to give off a photon of light with that amount of energy and thus a specific frequency. So this is kind of the picture of the model of the atom we've set up. We have all of these different allowed orbits, and orbits in between these are not allowed at all. So the electron can only jump discretely from these different allowed orbits. It cannot get closer to the nucleus than orbit 1. Each of these orbits has a particular discrete energy that's all given by this formula here. So as you see, we start off, the lowest orbit has an energy minus 13.6 electron volts. The second orbit out has minus 3.4 electron volts in energy. The electron will have minus 1.5 electron volts in the third orbit out, and so on and so forth. The further away, the closer it gets to 0. And eventually, if the electron had positive energy, it would mean it would escape from the attraction of the nucleus in the atom. So the experimental proof of this is to try to use these, find the change in energy that we need to jump from one orbit to another, and then find the frequency of the photon that would carry that amount of energy. Those frequencies should be frequencies that the hydrogen atom really likes to emit or absorb. So that's the last and final step here. So for instance here are all of the, you guys, if you've taken chemistry, you might have seen this before. But these lines here over on the right on the slide are representing our different allowed orbits. So here, this bottom line, this represents the energy of our n=1 orbit, our ground state. The second allowed orbit, the energy jumps up here. Third allowed orbit, the energy's here, so on and so forth. And then these vertical lines represent the electron jumping from one orbit to another. And in particular, the energy, if we wanted to find the frequency that an electron would give off by jumping from orbit 3 to orbit 2, we would have to take this energy difference and then set it equal to the energy of the photon and solve for the frequency. So the frequency being the frequency of the photon the atom would give off for the electron to jump between these two orbits. And you can go through and compute all of these possible frequencies for the electron jumping between any orbit you want. These are given different names in chemistry. The different frequencies for electrons jumping from energy levels back down to the lowest energy level or lowest orbit are called the Lyman series. All of the photons that are given off by the electron jumping from the higher levels all down to the second orbit are called the Bohr series. All of the photons that are given off by the electron jumping down to the third allowed orbit or energy level are called the PHY series. These are things that are calculated and tabulated in chemistry. All of these different jumps correspond to a different frequency of light the hydrogen atom would like to absorb. You can go through and take all these energy differences, plug them in here and solve for the frequencies and tabulate them all. But what we're going to do, we're going to take this and produce a general formula that will allow us to predict these frequencies. So here we're going to take two random energy levels or random orbits, which we'll call U and L. Those just stand for numbers of the different orbits. So if we want to calculate the photon that's going to be emitted by the electron jumping from orbit 3 down to orbit 2, that means U would be equal to 3 and L will be equal to 2. So if we want to get a general formula here, and I'm sorry for this change in notation, but my slides seem to change. On this next slide, U and L become M and N. But if we wanted to find the frequency or the wavelength of the photon that's given off, we just have to set Planck's constant times frequency, or converting to wavelength, Planck's constant times speed of light divided by wavelength is equal to the energy difference between the two levels, or between the two allowed orbits. And we could write that out pretty concisely as just the energy level of the lowest orbit times this difference, 1 over m squared minus 1 over m squared, n squared, where these two numbers, m and n, are the numbers of the orbits you're jumping between. So if we're jumping between orbit 3 and 2, here again, m would be 3, and n would be 2. And that will tell us the frequency or the wavelength, once we solve for lambda, of the photon that's given off in that process. Conversely, if we wanted to, this formula would also give the frequency of the photon that the electron needs to absorb to do the reverse jump is also the same. So what this formula tells us, if we plug in all the different values of m and n for the different energy levels of the hydrogen atom, we can compute all of the wavelengths or frequencies that the atom likes to emit or absorb. And this is quite a good estimate if you compare to the actual absorption or emission peaks for the hydrogen atom. This formula, called the Rydberg formula, is quite accurate. It predicts the photons the hydrogen gas will give off and absorb really, really well. It doesn't work very well for other atoms, so it's not a perfect model. But this model of treating the electron as a standing wave does give us a good prediction for what we see for hydrogen gas. I'll just run through one quick example in using these formulas for you. And then on Monday, instead of new material on Monday, what I'm going to do is, instead of class, I'm just going to be available from 9:30 until 10:30 during class time to help with homework problems, because I know this is not like an ideal lecture to do just in a recording. So before we finish, I will give you the section in the text that covers this material, and I will post these slides on Canvas right after I'm done here. And but I'll finish here with this one problem working with these formulas. So here we want to know if it's possible for the electron in a hydrogen atom to have a speed of 3.6 times 10 to the 5th meters per second. And then also, if we want a speed of 3.65 times 10 to the 5th meters per second. Are both of these speeds possible, or is only one possible? And if so, what energy corresponds to those speeds? And what is the radius of the orbit if the electron has that speed? So in order to start, we have to go back to the formula we derived for the speed of the electron in the hydrogen atom. Remember, it's proportional to 1 over the number of the allowed orbit. So the speed in the ground state, or the lowest orbit, is 2.19 times 10 to the 6 meters per second. So what we have to see here, if we knew the number of the orbit, we would plug in n and solve for the speed. Here we're given 2 speeds. So if we want to see if these are possible, what we have to do is take the speed, plug it in this formula, and solve for n. If n comes out to be a whole number, then it's possible. If n comes out, remember, n has to be a whole number. It can't be a fraction or a decimal or something in between. So if we plug these speeds into this formula and solve for n, the allowed speeds will give us a whole number for n. Non-allowed speeds will give us some fraction, some non-whole number. So let's try this with these different speeds. So for the first one, 3.6 times 10 to the 5th, solving for n and plugging in for the speed, that gives us n of 6.08, not a whole number. So that means in the hydrogen atom, there is no orbit allowed where the electron has this speed. If we plug in a speed if we plug in here 3.65 times 10 to the 5th, that comes out to be a whole number, just 6. So that orbit is allowed, and in fact, that is the speed of the 6th allowed orbit, or the 6th energy level in the hydrogen atom. So now we know for this speed, n is equal to 6. So if we want to go back now and find the energy of this orbit, we can go to our energy formula, which I'll put here. So the energy is minus 13.6 divided by the number of the energy level you're in, minus 13.6 electron volts divided by n squared. So here, the energy of the electron in the 6th allowed orbit will be minus 13.6 divided by n squared. So 6 squared is 36. Working that through, minus 13.6 EV divided by 36 will give you an energy of around, rounding here a bit, minus 0.38 electron volts. So if we want the radius of the orbit then, and I'll let you guys to finish this over here on your own, but the radius of the 6th allowed orbit will be equal to 6 times the Bohr radius. So that would be the last thing you need to do for that problem. From here, let me just double check this to make sure I'm not forgetting anything. And I am. So last thing for the radius here, if you want to find the, just want to check my formula. The radius of the orbit number n is n squared times the Bohr radius. So if we want the radius of the 6th orbit, it's going to be 6 squared, so 36 times the Bohr radius. The Bohr radius is 0.05 nanometers, so we're going to have 36 times 0.05 nanometers. Doing a bit of rounding. So the radius of the orbit the electron is in, orbit or energy level 6, is going to be 36 times 0.05 or 1.8 nanometers. So the electron is orbiting in the Bohr model, hydrogen atom here, at a distance of 1.8 nanometers away from the nucleus when it has this speed and the energy computed before. So that's where I'm going to finish today. I'm going to assign just a small number of problems on this topic this weekend. I know this is probably like a lot of stuff if you've never done it before for one online lecture, but on Monday, I'm not going to lecture. I'm just going to be available to help with problems. And then we will have our last new material on Wednesday. So thank you all for listening, and have a good weekend. I will talk to you on Monday.